Okay, welcome back to 373, everyone. Today we're going to continue our discussion of heaps, and we'll talk a bit about the end about preparing for software industry interviews, which some of you might be interested in. But we'll talk a little bit about that at the end and how this course relates to stuff you might see there. But first, in this video, I want to talk just about a brief couple announcements, and I want to review the story we've seen so far about heaps from Wednesday's lecture. So, as a reminder, since this is a video for Friday, Project Due is due tonight at 11:59 PDT. And then Project 3 will also come out today. Just like Project 2, this is also a 2-week project. And it is very related to the stuff we're talking about this week. So part of this project is essentially just implementing this heap structure that we're talking about this week. Now, to kind of give you a brief rundown of kind of what our learning objective looks like today. We're going to continue the learning objective from last time, which is being able to trace the remove, min, and add methods on the priority queue ADT in the heap implementation, specifically talking about those percolate down and percolate up methods. We also need to be able to describe how we can store heaps in slightly different ways that we'll introduce in this video today, or in these videos today. And then we also want to talk about this special type of algorithm called the build heap algorithm. So these are kind of our 3 learning objectives. They're going to be broken up into our 3 main videos for today. So first, let's do a bit of review of what heaps are, how we implement them for this priority queue ADT. So as a reminder, the priority queue ADT is somewhat like a queue where you can add values and remove them, but it's very different in the sense that there's a priority in each element. And we define our queues, our priority queues, to always return the minimum value. So we define that the value with the highest priority is the smallest value. So we're going to have methods like remove min and peek min to look at the smallest value. Again, I mentioned this last time. You could totally define this in terms of max values instead. It's just like flips everything we say around, but it's all the same logic. But just so we're crystal clear, we're always talking about minimum elements in this course. And we talked about one way of implementing this ADT is with this idea of a heap. And remember, a heap is a special type of tree. And specifically, we talked about binary heaps, which had 3 invariants. They're a special type of tree that's called a binary tree. So every node has 2 childs. That's the kind of tree we're most familiar with. And then, somewhat like a binary search tree, it has an invariant about the ordering of the data in the tree. But instead of being really strict like the binary search tree, which said all the values to the left must be less than, all the values to the right must be greater than, we have a much looser invariant here, which just said every node is less than or equal to all of its children. So it's kind of structured from smallest to largest going down, but there's not much structure enforced within each row. However, we do add one extra structure invariant called the heap structure invariant, which says that every heap must be a complete tree. And as a reminder, a complete tree is one that's completely full from each level down, except possibly the last row, where all of the nodes in the last row must be as far left as possible. So we talked about an example, the first 2 trees on the left here are binary heaps, but this tree on the right is not because it's not complete. Okay. Then we talked about, okay, well, if I have this idea of a binary heap, how can I use it to implement the priority queue ADT? So, for example, you could imagine, well, how would I do peek min? We said, well, that's just going to be the value at the top because the smallest value is going to be at the root of the heap. So very, very straightforward, constant runtime. That's great. When we talked about removing the min, we kind of outlined a 3-step process. The first step is actually removing the min value from the top that we're going to return. Then we do this kind of strange thing where we take the last node added, so the bottom row, the furthest right node, grab that and move it to the top. But this is most likely going to, while it restores the structure invariant, because now we have a complete tree, it breaks the heap invariant because we've now put a node that's probably larger than its children at the top. So then we fix this with a percolate down operation. And percolate down just lets that value we just put at the top fall down to wherever it goes in the proper place in the heap. And the way we do this is we always swap it with its smallest child. So we look at 13 and then compare it to its 2 children, 4 and 7. 4 is the smaller child, so we swap them. And we just keep doing this until 13 lands in its right spot. So we check if 13 is smaller than its children. It's not. Its smallest child is 5, so we swap them. We check if 13 is smaller than its children. There's only 1, but 13 is bigger than 11, so we swap them. And since it's a leaf node now, we stop. It would also stop if you, for example, hit a place where both of your children are greater than or equal to you. Now, in terms of the runtime, we'll talk about this a little bit more. This is really bounded by finding that last element and the time it takes to drop it down, to percolate it down. And this is a motivator for why the height of the tree being limited was so important. Now, as a reminder, why do we always have to choose the smallest child? And this is precisely to meet this heap invariant. Because if you chose the 7 in that example, and you put the 7 up top, well, then the 7 would be larger than the 4, its other child. So if you always choose the smallest child, you're always going to be getting a little bit closer to restoring that heap invariant. Now, the other operation we talked about on Wednesday was the add operation. How do you add a new value? And just like remove min kind of lets you percolate a value down, add is kind of like the opposite operation. You stick it at the bottom and then let it percolate up. So we start by adding it in the last available spot. So wherever kind of the, try to make it as left as possible in that last row. We add it there and then let it bubble its way up, percolate up based off the value. So just like percolate down lets you keep swapping down until you reach your right spot, percolate up is the exact opposite. So we keep fixing the heap invariant by swapping this node until it reaches a place where its parent node is smaller than it. Just like remove min, this is going to end up having a running time that's bounded by the height of the tree to find that place in the last node and then percolate it up. To talk about this a little bit more concretely, here is a new slide that I didn't quite show you last time. To kind of summarize these two runtimes, the remove min operation had these 3 components. Removing the root node, which is a simple O of 1 operation to just change a reference. But then we had to go find that last node, which would require traversing down the tree of height log n, and then percolating, once we place it at the top, percolating it down, which in the worst case would take log n time. So this is why on this table on the right, I show you in the worst case, we have this log n runtime for percolate down. I'm not going to really talk too much about the best case, but you can imagine we'll see in our next implementation, if I can really speed up that finding that last node, which is definitely possible, you could consider a best case priority queue is one that all of the values have the same priority. So then when you put it at the top, you never actually have to percolate it down. So again, that's not bounding the number of elements there. You could still have a really big tree, but if they're all the same element, then you never have to do that percolate down, which would take log n time, assuming you know how to get that last node in constant time, which is not quite always clear with our current implementation. So that theta of 1 best case is actually kind of hard to reach right now. Now, in the add case, we find the next available spot and insert a new node. That's also going to take O of log n time. And we then percolate it up. In worst case, we're going to go all the way up the tree. So what I want us to talk about in our next video is a different implementation of this idea of a heap that helps us speed up this case of finding the last node or finding that empty spot to place it in. Notice this implementation I'm going to talk about isn't necessarily going to give us any faster asymptotic time. So it's still going to have this log n behavior in the worst case, but as a bit of a hint, it's a structure that takes advantage of instant array accesses so that we can better find where this last index is more quickly. But that's a bit of a spoiler. We're going to talk about that in our next video.